In this example, we're asked to find the weight of a spaceship on the surface of Saturn, also known as the force of gravity. They also ask in part B for the acceleration due to gravity on the surface of Saturn, which we would consider as the field strength of gravity. So let's start by writing out what they give you. Give you the mass of the spaceship, and that's 1,000 kilograms. We have the mass of Saturn, which is 5.67 times 10 to the 26 kilograms. We have the radius of Saturn, which is 6.0 times 10 to the 7 meters. So for part A, they want the weight of the spaceship, which is also known as the force of gravity, which we have an equation. It's Newton's universal law of gravitation. Big G, the mass of the first object, we'll call that Saturn, the mass of the second object, the spaceship, over the distance between them, which in this case would be the radius of Saturn. So I'm going to plug in the values I have here. Big G is a constant, 6.673 times 10 to the negative 11. The mass of Saturn is given in the problem as 5.67 times 10 to the 26 kilograms. The mass of our spaceship is 1,000 kilograms. We're going to divide the whole thing by the radius of Saturn, 6.0 times 10 to the 7th. We need to square that radius. So I'm going to open up my calculator, and I'm going to type in. I already have alpha G, have G stored in there as 6.673, so I don't need to type out that value. 5.67, second E, that is times 10 to the, and raise it to the 26th power. Calculator's being weird. There we go. Times 1,000, which is the mass of the second object, which is the spaceship. And we'll divide it by 6.0 times 10 to the 7, and we square it. Again, when you use that double E feature, it assumes you typed out all the zeros, so you don't need parentheses, so I can just square it, and it'll handle it correctly. And I get a value for the force of gravity of 10,510 newtons. So Fg, the weight of the spaceship, is 10,510 newtons. That would be our answer for part A. For part B, they want Ag. And we have a separate equation for Ag, but remember Fg is just mass times Ag. And the mass would be the mass of the spaceship. So if we know the force of gravity, we could just divide. We know Fg is just mass times Ag. So the force of gravity on the spaceship would be the mass of the spaceship times the acceleration due to gravity. And we know the force of gravity of the spaceship. We just found it. So I can use that previous answer. And if I just divide by 1,000, I get my answer as 10.51 meters per second squared, which is a little bit more than what you would find on Earth, which is 9.8 at the surface, which makes sense. That is a bigger planet with a little more mass. Now, the other way you can do it is to use our field strength formula, which is to say that Ag is just big G, the mass of the object creating the field, which would be Saturn, over the distance to the center of that object. So that would be big G, 6.673 times 10 to the negative 11, times the mass of Saturn, 5.67 times 10 to the 26. That's the object creating the field. And the distance to the center of that object is 6.0 times 10 to the 7, and that object would be squared. So my calculator, I already did that big calculation. I'm just going to hit second enter, and the only thing that changes is I remove that 1,000 in there, which again, you see mathematically, I've really just divided by 1,000, and I get 10.51. So again, two different ways to find that acceleration, which is in meters per second squared. You could also find the acceleration first and then multiply by 1,000 to get the force. Because again, mass times acceleration is the force of gravity. So I hope this is helpful. Stay tuned for more videos.